In this review video, I'm going to be talking about Gauss's law. And what Gauss's law tells us is that the electric flux is equal to the closed integral of E dot dA. And we also know that flux is equal to the Q enclosed over epsilon naught. Now, one thing that we know about flux is that the flux is the total amount of E-field lines that go through a Gaussian surface, which is basically the surface where you're trying to find how many E-field, like the intensity of how many E-field lines go through. So say we had a point charge, and say it's a positive charge. If we draw in our E-field lines, it would look like that. Now, if we're trying to find the E-field at, say, this point, you would draw in a Gaussian surface that goes through that point. So if you drew a sphere here, this formula will tell us the total amount of E-field lines that go through this entire sphere. And with that information, we can find out our equation to find the E-field at one point. And so here, if we integrate E dot dA equals the total charge, which is a positive Q, over epsilon naught. Now, we can bring the E out because there's a constant, since each point on this Gaussian surface is equidistant from the charge. We know that the E field is the same at each point on this surface. And this dot, that means that we have to cosine, you have to do E dot dA cosine phi, where cosine is the angle between the two vectors. So say we had an area vector right here. Since the area vector is normal to the surface, and the E field at that point is also normal to the surface, phi is equal to 0, so cosine phi equals 1. So this basically just becomes E times the surface integral of dA. And since it's a sphere, we integrate from 0 to 4 pi r squared, since that's the surface area formula for a sphere. And now we can just set that equal to Q over epsilon naught. And now if we integrate this, we get E 4 pi r squared equals Q epsilon naught. And now if we solve, we get that the electric field at this point charge is equal to Q over 4 pi r squared. Well, let's put epsilon naught before. 4 pi epsilon naught. Now if we go back to our Coulomb's law for the electric field, we know that electric field is equal to kq over r squared. And so if we compare these two equations, this one using Gauss's law and this one using Coulomb's law, then we see that k is just equal to this, 1 over 4 pi epsilon naught. And so that's one way to derive Coulomb's law using Gauss's law. Another important thing to know about Gauss's law is that this Q is not the total Q in the whole entire problem, I suppose, but it's the charge that's enclosed by the Gaussian surface. So, say you had a charge here, a charge here, a charge here, a charge here, but your Gaussian surface was like this. like that. This surface does not enclose any charge, therefore the flux is equal to 0. Likewise, if you have, say you have two charges, positive Q and negative Q, and if you draw the E field lines, it would look like that. Like that. But, and then say your Gaussian surface was like that. The total charge enclosed equals positive Q plus minus Q, which is 0, which makes flux also 0. One important application of Gauss's law is in conducting spheres or shells. What was discovered using this law was that if you had a charged conducting shell, say there was a shell like that. Actually, let me just draw better. There's a shell like that, and say this was the shell. If it's conducting, all the charge goes to the surface of the conducting sphere. And so, from the center up until the surface, there's no charge anywhere here, so there is no flux at all. And this was also confirmed through an experiment where a person sat inside of a charged box and did not get shocked because all of the charges went to the outside, and so there was no flux in the inside of the conducting shell. Alright, so now we can do the derivation to find the E field of an infinitely charged wire. So say we had an infinitely charged wire that looked like this. And assume this wire is straight, even though it doesn't look that straight. And assume that this charged wire has a uniform charge density. So lambda equals Q over L. L being the length of this hypothetical infinitely long charged wire. So now, in order to find the E field, we have to add our Gaussian surface to the problem. So what we can do is make a cylinder, our Gaussian surface. So it would be another thing like this. It doesn't look much like a cylinder, but it's a cylinder. And so now we can use Gauss's law to find what the E field is. So the E field is, well, flux is the surface integral of E dot dA, and we know that's equal to Q over E. Now, since we know that it's a uniformly charged wire, we can say that Q is equal to lambda L, and we can substitute that in here. Now, since it's a long straight wire and the cylinder is equal distance at all points and it's uniformly charged, we know that the E field at each point on the Gaussian surface is going to be the same. And we also know that it's going to be parallel to the area vector. So we know we can basically get rid of the dot. And so now we just have E integral of dA equals lambda L over epsilon naught. And let's say the radius of this cylinder is little r. And so the area of this cylinder, we know the area of the cylinder is just the circumference of one base times the length of the cylinder. So we can integrate the left side of our equation. So we get 2 pi RL and then E. equals lambda L over epsilon naught. So now all we need to do is solve for E. So we get E is equal to lambda L over 2 pi r L epsilon naught. And the L's cancel out, so you get E is equal to lambda over 2 pi r epsilon naught.